Hi everybody, I'm Wadekar. I'm a postdoc at the IAS, and today I'm going to talk about gas-rich dwarf galaxies and using them as calorimetric dark matter detectors. This is work done with people at NYU. So the first work was done with Professor Glenn Farrar, and then we did a follow-up with PhD student Ziwei Wang, who is going to graduate next year. So let me first give a brief motivation of using dwarf galaxies to probe dark matter. As I think most of you already know, baryonic feedback in dwarf galaxies is weak. So we can use them as pristine laboratories for studying non-standard interactions. Also, there are a lot of popular alternatives to cold dark matter that affect abundance of dwarf galaxies. For example, fuzzy dark matter or self-interacting dark matter or warm dark matter. Let me put our work in context. Dwarf galaxies have already been used to probe dark matter annihilation or dark matter decay. In particular, people have used dwarf galaxies which are closer to us and do not have gas. And one way to probe dark matter particles is if you have annihilations at the centers of these dwarfs, you can produce standard model particles, which can then produce observational signatures like gamma rays, which you can use observatories like Fermi-Lat to detect. This has actually led to like one of the strongest bounds on the WIMP annihilation scenario. So what you can also probe with these dwarfs is dark matter decaying to standard model particles. But for dwarfs which do not have gas in them, you cannot probe interactions of dark matter directly interacting with standard model particles because there are very few baryons. There are stars in the in these galaxies, but the stars have very small cross sections. So we were thinking of other types of dwarf galaxies which are gas rich, and in these dwarfs you can probe directly interactions of dark matter with standard model particles. So if there are interactions of any kind where dark matter exchanges heat or interacts with plasma, the neutral hydrogen gas in the galaxies, you can try to probe these kinds of interactions. So let me place these galaxies in context observationally. So you have, for the low mass dwarf galaxies, which fall inside the virial radius of the Milky Way, they do lose their gas due to ram pressure stripping. But then we have, with the advent of high resolution surveys, we have now started detecting gas-rich dwarf galaxies, which are away from, like further up, away from the virial radius. And with upcoming surveys, these detections of these will accelerate. So one important property of these gas-rich dwarf galaxies is that they have ultra-low gas cooling rates. Here I've shown on the y-axis the gas cooling rate of gas in systems. So here are the gas in the Milky Way environments as compared to the cooling rate of gas in a particular galaxy that we study called LEO-T. And you can see the cooling rate is much lower than others. One way to understand this is you can write the cooling equation for the gas in astrophysical systems as number density of hydrogen squared times a function of temperature times the fraction of metals. And this quantity makes like these gas-rich dwarf galaxies special because the metal fraction of these like gas in them is very low. And so one way to think about it is if they have low metals, you have less lines available for cooling, as essentially you're cooling using electrons in the plasma interact with atoms like carbon or oxygen, which can then emit radiation. So then the question that comes to mind is, if they have such low cooling rates, can you use them as calorimetric dark matter detectors? if dark matter injects any energy into the gas, this seems like they should be very good candidates. And so we follow a conservative procedure where we require that the dark matter heat exchange rate is smaller than the rate at which the gas can cool, or the gas cooling rate. And the logic here is that a system which has low gas cooling, it's very hard for it to dissipate an additional heat injected into it. And we use this procedure to constrain a lot of dark matter candidates, some of which have been recently popular. For example, if dark matter decays to photons or electron positrons, like some of the axions or axion-like particles, dark photon dark matter, primordial black holes, or millicharged dark matter. So I don't have time to go into details of all of this, but a common theme that runs through all these candidates is they do exchange heat with the gas. So let me give a brief overview of some of these. So for example, if you have dark matter particles which can decay to say UV photons, these UV photons can get absorbed in the gas in these gas-rich dwarf galaxies and lead to heating. This actually leads to very strong constraints on the decay of axion-like particles in a particular range where they emit UV photons. So here I've shown our limits in black as compared to other limits in the literature, for example, the CMB. And these constraints are, so on the y-axis, I'm plotting nearly square root of the lifetime. So these are sometimes actually an order of magnitude stronger. You can also follow a similar procedure where if your dark matter decays into, instead of photons, electron positrons, they can then heat the gas by colliding with the plasma. And we do get quite strong constraints. Again, I'm showing our limits in black as compared to other limits. And you can see that for these low dark matter masses, our limits are nearly an order of magnitude stronger than the current literature. So you can also do a similar study for ultralight hidden photon dark matter. So in this case, hidden photons can convert into standard model photons in plasma. This can lead to electric fields in the plasma, and electrons get accelerated, and so then they can heat the plasma by dissipating their kinetic energy. And here I've shown a mixing parameter in this model as a function of the dark matter mass, and our limits from one of these dwarf galaxies, Leo T, again, is one of the strongest in a big chunk of parameter space, as you can see. You can also have primordial black holes inside these dwarf galaxies, which can heat the gas. So for example, if you have black holes of greater than a solar mass, you can produce outflows, you can have dynamical friction, or you can also produce radiation coming from accretion disks. And by requiring that this heating is less than the rate at which the gas can cool, some groups have suggested very strong limits on these candidates. So the limits I've shown from Leo T is in blue. So the studies on the left hand side are not our studies, but these studies used these similar gas-rich dwarf galaxies and then tried to constrain these primordial black holes. In the lower panel, I'm showing black holes of much smaller masses, but which can also be probed by this method. We are actually currently working on other kinds of compact objects which can be probed by these gas-rich dwarf galaxies, and we are looking at if primordial black holes have small magnetic charges in them, can you constrain them? So this is work in progress. So a common theme that runs through these candidates that I mentioned is that all of these candidates heat the gas in some way. And so I think this is a general pipeline for setting bounds on candidates that can transfer energy to the gas in some way. And I think the pipeline is quite simple. You have these parameters for the gas in the galaxy, which are well calibrated from observations. And you can require that the heating rate is smaller than the radiative cooling rate of the gas in this dwarfs. So if there are suggestions for more dark matter candidates, I would be very glad to hear them. Okay, so before I wrap up, let me talk about some of the upcoming surveys of dwarf galaxies. And so one interesting thing is with the upcoming surveys like Rubin or HSC, galaxies like Leo T will be detectable up to nearly 5 megaparsecs. And also, there are also upcoming surveys like Roman, Wallaby, SK, which can also be used to detect these kinds of galaxies. So to give an observational picture, right now we can try to detect dwarfs in the field up to nearly 0.5 megaparsecs. But then once like surveys like Rubin come up, the sensitivity of detecting galaxies like Leo T, so absolute magnitude -8, will be like up to 5 megaparsecs. And so we will detect a lot more of these systems. And so I think it is interesting to think about what kinds of alternative to standard model scenarios we can try to probe using these dwarf galaxies. Some work along these lines that we are also thinking of is trying to use hydro simulations of these dwarf galaxies and then trying to inject non-standard dark matter models and seeing what happens to the gas inside these dwarf galaxies. So for example, if you have dark matter which can like inject some kind of heat, so we are using some of the older studies by List et al., where they used a bigger system which contains gas, and then they tried to inject annihilating dark matter into it, and then saw that the properties of gas in the galaxy changed. And we are trying to do a similar study for these low mass gas-rich dwarf galaxies. So let me summarize. Low mass gas-rich dwarf galaxies are very sensitive calorimetric dark matter detectors. And a particular galaxy, Leo T, gives strong constraints on a lot of popular dark matter models, dark photon dark matter, millicharged dark matter, or like dark matter decaying to electron positrons. And you can see the constraints are in black. Okay, thank you. And I look forward to interacting with some of you at the conference.